So I think what I'm going to do is start off with that gas density worksheet that I may have shown you last time, but I certainly didn't do anything about it. So let's go to that. It's just a kind of thing that you should be able to do in PChem. You should be able to, you know, manipulate the ideal gas law equation into doing different things. So let's see, if I share my screen, what happens here? Of course, I closed everything before when I shut down the computers. Oh, there I am. So hold on. Share screen. There we go. All right. Okay. Hold on a minute. No one's in the waiting room. All right. All right. So so this is a little, just a, you're not going to be able to see my face. That's life. I know it's not that terrible. Well, maybe you will be. I have the webcam. I'm all confused. But anyway, it doesn't matter. So this is a worksheet on gas density. And I just wanted to say that this goes through kind of a typical sort of recasting of the ideal gas law to show that gas density depends on molar mass and other things. So you should be able to sort of ooh, that's a nice color, recast the ideal gas law to deal with things like gas density and to come up with a formula for the molar mass. So I thought we would go through this, this little gas density worksheet. So what we're trying to do is find a relationship between gas density and molar mass, and it's going to involve some other things from the ideal gas law as well. And if you can do it without using this worksheet, then that's terrific, you know. But what you would do is you would start, you know, with the ideal gas law, PV equals nRT. And if you're looking for gas density, you'd say, oh, okay, gas density, that's mass over volume. So maybe I better put mass in this equation. And I'm going to have to put molar mass in this equation. So which of these quantities is most closely related to molar mass? You say, well, moles. Moles is mass divided by molar mass, right? Grams over grams per mole. So then you could substitute this for the moles, right? And once you did that and you had PV equals M over MRT, you could say, oh, if I put the molar mass over here, I have PM, and then I could divide by the volume, and lo and behold, this is the density. So that's what this whole worksheet is doing. It's really just takes you through that calculation. And if you can't, you know, if you can't, you know, do it all at once like this, if you go through these steps, this is just sort of walking you through how to do it. So this is exactly what I just did. This is mass over molar mass, which you would then substitute for N into the ideal gas expression. And then you'd think about the density and you'd say, okay, what is density? So you know it's mass over volume. So you'd see this volume over here and you say, oh, I really want that on this side. And why don't I take the molar mass up there at that point? So D is M over V, that's what I wanted here. And then, so then you'd have PM equals M over V RT. So that's what I'm looking for. PM equals DRT. So the pressure times the molar mass is the density times R times T. And then you could actually even rework this and you could divide both sides by the pressure. And then you could put in mass over volume for the density. And this equation is one we use in general chemistry, which maybe if you were at RIC, you saw that experiment, you did that experiment where you take a canister and you weigh it before and after you dispense it into an inverted cylinder, filling it with the gas. Okay, so this is water. And then you know the mass of the gas from the weighing the cylinder before and after. You know the temperature, you know the pressure, you know the volume, and you could calculate the molar mass of the gas. So this is another equation that is very closely related. It comes from the ideal gas law and is pretty easy to derive. So anyway, I'm not going to do a whole lot of gas law problems. I'm not going to do any of them really, but that doesn't mean you don't need to know how to do them. So there's some in the homework, there's some in the text in the homework, and you know, you should be practicing that. So if you noticed, I posted assignment 1. I think it was sometime last week. I forgot to tell you about it during class, but I'm sure you've had a look at it, right? You've had a look at it, right? Some of you, good. All right, so what I'm going to talk about next is something a little bit different from what I've done so far, and maybe you've been reading in Atkins, and you've been hearing the terminology where he says that this is called an equation of state for an ideal gas. And I thought I would show you kind of visually what this means. So I'm going to show you what this means in a couple of different ways, because it is a little bit of a funny way of putting it. What does that mean, an equation of state of an ideal gas? So what does that mean? So let's consider a mole of an ideal gas. And let's say that the temperature is 273 Kelvin and the volume is 20 liters. And let's say that the pressure is 2 atmospheres. Does anyone have a question about this? Can you look at that and see that there's something wrong with it? So here's my question. Is this a set of P, V, T, and N that is possible for an ideal gas? Who said it?
Be one?
I didn't hear that. Say it again.
I said, shouldn't the pressure be equal to 1 atmospheric pressure?
Yes, it should be. It should definitely be closer to 1. And that's, you know, and that's why it's not right. But what I'm trying to do is explain this expression to you, the equation of state, and what it means to be an ideal gas. What is this? So here's the question: is this set of P, V, T, and N? We all know the answer to the question, but let me reword it as: is this set of P, V, T, and N possible? And we've already heard that it's not possible. But another way of saying this would be to say, is this set of P, V, T, and N, this set of variables, is it a possible state? Of an ideal gas, of the gas. So these are actually equivalent statements. Is this set of variables a possible state of the ideal gas? So that tells you what it means, what a state of the ideal gas is. It's really just defining the parameters of a particular gas at a particular, you know, time, okay? And not all states, not all sets of P, V, T, and N are possible. So the reason why you know that this set is not possible is perhaps you know that 1 mole of an ideal gas at standard temperature and pressure, which is when you have 1 atmosphere, would be about 22.4 liters. And this is 2 atmospheres, and yet it's pretty close to 20 liters. So if you take pressure and try to figure out, does it equal nRT over V, you know, you'll see that you have 1 mole, you have 0.08206, you have 273, and the volume I said was 20. And you could see when you work this out, so I said the pressure is 2. This comes out to 1.1 atmospheres. So they're not equal. So that means that this set that I said, that set of P, V, T, and N are not a state, are not a possible state of an ideal gas. Okay, now there's a great way to show this visually, and it kind of has to do with what we were talking about last week, which was the total differential dF of a 2-variable function. You know, it's such a nice example that I can't pass it up. So here we have P is nRT over V. Now, if I say that N is constant at 1 mole, okay, then that means that P can be thought of as a function of temperature and volume. Okay, N doesn't enter into it, R is a constant. Okay, so that means that T and V are like X and Y, right? That's like the XY plane. So if I put pressure here on the Z axis, here volume and temperature. Okay, so this is like the VT plane down here. And every one of the points in this plane, right, has a pressure value, you know, go up to a certain P. And you would make a surface, okay? So the P's are points on a surface above the VT plane. And I'm going to show you that, what they look like when you connect the points and make that surface. So here I have that surface. This is what it looks like. And just to show you what I mean about this point, right? This point is the one I was telling you about. 20 liters, 273 K, and 2 atmospheres. And it's not on the surface of possible states. So this sort of turquoisey blue surface, this represents all possible states of an ideal gas. Okay. So, so you could see that if I make that pressure 1.1, now it's on the surface. So all of those allowed pressures connect together and it looks like this. Do you believe me? So how can we, you know, without just believing me, right? How could we show, how could we prove that this is the right surface? So how do I know this is the correct surface? So what would be certain characteristics of this surface? So what could I do to investigate that? So here's a picture. Okay, and this shows that surface, but now it's done some things to that surface. And this is what sort of speaks to some of the stuff we were talking about last week. So what happens if I take and I slice this surface at constant values of the volume? So that's what those red lines are representing. Or if I made cuts to this surface, so you were looking at how the pressure depends only on the temperature. Okay, you could see that you have a line here, and then you have a line here, and then you have a line here. Okay, so how do I know that's the way it should be? So if I cut the surface at constant volumes, so now we're looking at P as a function of T only. Okay, so we know that P is nRT over V, and the slope dP dt at constant V, that's what that means, at constant V, If we take this derivative or this partial derivative, we know it's nr over v. Now, v is constant here, v is constant here, v is constant here. So nr over v, these are all constants. So that means the slope isn't changing as the temperature is changing. So what type of a curve does it have to be?
Linear.
And it is a line, yes. So this shows this constant slope means that this is linear. And that checks, right? Because these are lines. Okay, so that's one piece of information that supports the fact that that particular surface is the surface that represents the states of an ideal gas. You can also see that as this value of the volume increases, as we go that way, let's see, oh, that's decreases, sorry. As the volume decreases, these slopes increase, right? It gets steeper. So this is smaller v, steeper slope. And that makes sense too, because this volume here is in the denominator, and as it gets smaller, the slope gets bigger. Okay, so that jives as well. That makes the surface, you know, us think that this surface does look sort of like the right thing. So what about the rest of it? So the second thing I could do is I could come over here and I could cut the surface here. Cut the surface at constant values of the temperature. And now I could look at P versus V. And so what about this? First of all, the red curves are all positive. They're all positive slopes. There's nothing here that's negative. Moles can't be negative, R is not negative, volume can't be negative. But first of all, I see that I have a negative slope. Okay, so look, P is nRT over V. What is dP dV at constant T? It's minus nRT over V squared. This is something that we did in the calculus problems. Okay. So, so you could see that first of all, you have a negative. These are all negative slopes here. And let's see, what else was I going to say? And also, as the volume increases, so as you're going down here, as the volume increases, the slope gets less steep, gets less negative. And that's because you have this V squared in the denominator. So as you increase V, you increase that denominator, you're decreasing the value of that slope. So that's great. The negative sign is great. So, you know, that's evidence that this is the right surface, okay, for an ideal gas. All right, so that's just a piece of, you know, kind of P-Chem lingo kind of information. So to sort of move on with, well, actually to finish talking about macroscopic ideal gases, I need to tell you about Dalton's law of partial pressures, or at least review it from general chemistry. But the funny thing is that I'm actually teaching this in general chemistry right now. So I can't remember what I did in one class and what I did in the other, but we haven't done this here yet. So Dalton's law of partial pressures, you probably could tell me what it is, but I'll tell you instead. It says that the pressure exerted by a mixture of gases is the sum of the partial pressures that of each gas. We'll get to that in a minute. what exactly that means. And 2, that the partial pressure of each gas is the pressure that gas would exert if it were the only thing there, okay? The partial pressure of each gas is the pressure that gas would exert if it alone were present, okay? So the first one tells you that if you have three gases, let's say, you would add those partial pressures to get the total pressure. But the second one really gives you the information on what this is equal to. So the partial pressure, oh, I didn't open that, is that pressure that gas would exert if it alone were present. So if you had N1 moles of gas 1 and N2 moles of gas 2 and N3 moles of gas 3, okay, then P1 would be N1 RT over V, because that's the pressure that it would exert if you only had gas 1 in there. So that's why we end up with these equations for each of the different gases. Note, every gas occupies the entire volume. There's no V1, V2. That's not parceled out at all. We'd have P3, of course, N3 RT over V. And, you know, in P-Chem, we like to use fancy notation. So we go Ni RT over V for the partial pressure of the ith gas. And then we would say the sum over I of Pi is P total. And actually, you could see that if these are the definitions of the partial pressures, and you added them together, you'd have N1 RT over V plus N2 RT over V plus N3 RT over V. And you'd be able to factor out the RT over V. Okay, so you end up with N total RT over V. So that's what P total, which is the sum of the partial pressures, is given by this equation. So what this says is that we have an ideal gas laws for P tote relating to N tote. So we have an ideal gas law for the whole thing, for the sum of the moles. And then we have ideal gas laws for each component, Pi and I RT over V. And another thing is, if you look at how the partial pressure relates to the total pressure, this ratio, that's just Ni RT over V divided by N total RT over V, and everything cancels except for Ni over N total. Ah. Oh man, what did I do? Okay. All right. So this, by the way, anybody know what this is called? Nobody? No, really? That's called a mole fraction. Xi. Okay? So that means that the ratio of the partial pressure of one gas to the total pressure is the mole fraction. So you can take the mole fraction, multiply it by the total pressure, and that gives you the partial pressure. So A lot of times in problems like this, there's more than one way to solve the problem because of these different relationships. All right, so I do have one example. Here it is. I'd like to collect this on Wednesday. I'll probably put something on Blackboard for you to post your answer. And so let's take a look at this problem. So here we have a problem. It's just a gas phase reaction. It tells you the volume of the container. It tells you the volume is fixed. So it's not one of these movable wall kind of problems. The temperature is constant. Initially, there's a pressure of 1 atmosphere, but the pressure is going to change in this reaction. I guess that's kind of what I want to ask you. What happens to the pressure during this reaction? Anybody?
Wouldn't the pressure go down?
All right, look at these mole things here. So,
Sorry, no.
yeah, remember all gases behave the same, right? And what matters is the total number of moles that you have there, okay? So, you know, it tells you initially you only have this compound, the reactant, okay? But as the reaction goes on, every 2 moles of that react generates 6 moles on the product side. So you have this fixed volume, you have more moles being generated, and so the pressure is definitely going to go up. So volume isn't changing, T and R aren't changing. The only thing changing is N total, right? And so and what happens to it, it goes up. Why does it go up? And that's because there's more moles of the products, okay? So we know the P total is going to go up. So if the reaction were to go all the way, it doesn't, but what if it did? What would the final pressure be? So that's what this problem is asking you. Yeah, of course, it's easier to determine that than to do an equilibrium problem, which we're not doing. So what you should do to practice this kind of partial pressure problem is figure out the moles of BRF5, right? Because we know that P total is N total RT over V. So you can use this to solve for N total. Okay. And then you can use that to calculate the moles of product, right? That's like a Gen Chem problem. You're using a mole ratio to get each of those moles of products as 2 products. And from moles of products, you'll get the total pressure using, again, this equation. And then you'll be able to figure out the partial pressures as well. And I want you to do it this way, even if you could think of a much faster way to do it. So what's the faster way to do it? I want you to do it both ways when you hand it in, right? But what would be the much faster way to do it? So we go back to the equation here.
Couldn't you take like the partial derivative?
No, not something so complicated as that. So what's the only thing that's changing on the right side of this equation?
The moles.
Yeah. And what's happening to the moles?
It's increasing.
By a factor of what?
Three.
Yeah. So when you do this part, you should figure out that the total pressure is going to be about 3 atmospheres. Okay? And here you will just figure out that you have to multiply by a factor of 3, and you obviously we get the same thing, but I still want you to show me this. Now, I want to tell you that not always are these partial pressure problems so straightforward. So here's assignment 1. And I just want to point out this particular problem here and show you why it's different and why this one is a bit harder. Okay, or maybe you could tell me why it's harder. Here, I circled one thing. Okay, so if you look at this problem, here's the coefficients. Just tell me, why is this problem harder? No takers?
Dr. Cooley, I don't see anything on your screen that like it. I still see the previous worksheet. Like I haven't seen anything changing.
Oh, is that true for everybody?
Yeah.
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 Like you were showing us what you wanted to do, but
when did that happen? When did that happen?
it happened a little while ago, actually.
Oh, great.
I thought it was just me.
Well, I must have hit something that paused it. So where should I go back to?
Right there is like where it froze.
Okay. So, so I was just telling you how to do this problem and what the answer would be. Pretty nice of me, I think. All right. Anyway, I think I'll post the notes so you'll be able to catch up on that. But now let's look at this problem, all right? And tell me, why is this one a little bit harder than the one before it? By the way, I hope you appreciate the scene behind me. Do you appreciate it? It's the rocky coast of Maine. I haven't been there all summer. It's near where my mother lives. I think I probably told you that already, but that's all right. I'll tell you again. So why is this problem? Yes.
Because the number of moles go, is it because the number of moles go down? Like you had 3 before on the left-hand side reactants and then 2 on the.
Who's talking? How come I can't? Is that Jack?
Yeah.
Oh, okay. So what are you saying? Why do you think it's harder?
Is it because like the reaction is going from more moles to less?
Well, you're kind of right, but I don't know that you're right for the right reason. It's not so much that the moles are decreasing. It's going from, 3 moles on the left to 2 on the right. That's not what makes this problem harder. Is there are 2 reactants, but they're not present in the stoichiometric ratio, which is 2 to 1. It's present in a 1 to 1 ratio, right? So what does that mean is going to be true at the end of this reaction? So in this example here, you had reactants at the beginning and they all reacted away. And at the end, you had all products. You didn't have any reactants left over, right? I said it goes to completion. But this reaction, I'm also saying, let's assume this reaction goes to completion. Let me write that down. But at the end, at completion, what are you going to have in the reaction vessel?
You're going to have some product and some reactant.
Yeah, you're going to have leftover. One of these is going to be left over, right? Because you need twice as many moles of CO as O2. And so since you only have 1 to 1 mole ratio present, and by the way, you're given the pressure at the beginning. And if it's a 1 to 1 mole ratio, you could easily figure out the moles of each. They'd be the same, okay, whatever they are. So this is a much more difficult problem to do because you have to, figure out the moles at the end of the products, but then you also have to figure out how many moles of reactants you had left over. And that's also present. So you have to add that up to get the total moles. Okay, so make sure you know how to do this kind of problem as well. Okay. So that's what I have to say about Dalton's law. And let's see, what time is it? It is 4:39. All right, so I have a little time to start this next thing, which is the kinetic theory of gases. So I'm going to go to another window here and do that. All right, so what I call this part of this unit, I call it a microscopic diversion. Because everything we've done so far has been about the behavior of a large sample of gas. You know, what happens to the volume when you change the pressure? This is something that's a characteristic of, you know, a rather large volume of gas. You're not going to, you don't know, you can't answer those questions when you're talking about, you know, a collection of a bunch of a few molecules. It's just not something, it's something that manifests itself in nature when you look at, you know, big things happening with large collections. So this microscopic diversion, it's in another chapter entirely. It's in, I think it's chapter 24. It's just a few pages there, but I'm going to go over what you need to know from it. And I call this the kinetic theory of gases. And believe me, there's many ways to study the kinetic theory, and we're going to do a pretty lower level version of it, but much different, it's a higher level than what we did in general chemistry. So what I'm going to do is I'm going to lay out some characteristics of gas molecules, and we call these postulates. So we're going to make some statements about gas molecules, and they're going to seem pretty logical to you, I think. Okay, and then what we're going to do is we're going to use them to try to deduce some things about the behavior of a macroscopic sample. So to deduce the behavior of a macroscopic sample, like the kind we've been thinking about, okay? So we want to deduce that behavior from microscopic considerations rather than just, you know, write down laws based on observations of those macroscopic things like pressure, temperature, and volume. So we'd like to start with the molecule. So here are the postulates. A gas consists of molecules in continuous random motion, so they're always moving. Gas molecules don't stop and take a rest, okay? Another statement is that the size is really very, very, very tiny compared to the container that they're in, okay? So that's another postulate. And a third one here says that gas molecules do not interact except through brief, infrequent, and elastic collisions. That means there's no energy loss to the environment, okay? No friction, no heat, that kind of thing. And same is true with the collisions with the wall. So what we're going to do is start with these three postulates, and we're going to calculate the force of one molecule making a collision with a container wall. Okay, we're going to do this by calculating the change in momentum. I call this the force per collision. Then what we will do is we'll figure out the total, the total number of collisions with the wall in a time interval, delta t. And we'll have to do that by considering the number of molecules in the sample, and that's what it'll start with, but you'll see. Then what we'll do is multiply those two things together. Force per collision times the number of collisions, and that will give you a total force. And we'll divide that by the area to get the pressure. So that's the basic idea of what I'm going to start to do. I don't think I'll be able to finish it, but I'll start to do it today. So I want to start with this force per collision. All right. So force, Newton's second law, F equals ma, mass times acceleration. But the acceleration is actually the derivative of the velocity with respect to time. So, so I could actually bring this mass inside the derivative because it's just a constant. And so we could think about the force as the change in momentum with a collision. That's because we want the force per collision. So we're actually looking to get the change in momentum over the change in time. So what I want to do is think about a wall and a particle colliding with that wall. So here I have a wall of the container, and I'm going to make that wall perpendicular to the x-axis. And I'm going to kind of draw a before and after picture. So here's the before. Here's going to be the after. And here's my particle. It's going this way. And what I'm going to do is do an easy example first. So the easy example is if my velocity vector of this particle, if it only has an x component, that's what I drew here. It doesn't have a y or a z component. I'll get to that in a few minutes. So before it hits the wall, it's traveling in the direction of the arrow along the x-axis, and its momentum, mv, is mv sub x, because it only has the x component. So after this particle hits this wall, and it's now going in the opposite direction, okay? So after the collision, what is the one thing that changes here, right? This component changes to its negative. You see that? So now the momentum is minus mvx. And when you take and you look at the change in momentum, it's going to be the final minus the initial, or minus mvx minus mvx, or minus 2 mvx. But I'm really only interested in the magnitude of this thing. I'm just going to call it 2 mvx. So that's the change in the momentum for that collision. So, you know, what the next logical question might be, well, what if it has a y component or a z component? Okay, so let me add one of those components here. I'll add the one that's easy to draw. Okay, so here I'm going to draw my wall again twice because I'm going to do before and after. And now here's my particle, and it's going this way. So it's not going perpendicular to the x-axis. Let's say it's going like that. So it's got two components, right? This is its Vx, and this is Vy. Okay. So after it hits this wall, it's going to bounce off. Which way is it going to be going? What's going to happen to the x component? And what's going to happen to the y component? So before, it's Vx, Vy, 0. After, what is it? Well, this particle is going to hit this wall, and it's going to go like that. So it has, the x component changes. But what about the y component? Does it change? We know what's going to happen when it hits the wall. It's going to go choo, choo. The y component's still pointing down. So after this collision, it's going to be going like this. okay? Its x component is going to be the negative of what it was, but its y component is the same. So it's going to be negative Vx, Vy, 0. So the only thing that changed was the x component. So again, the change in momentum is minus 2 mvx. It's as before, because the momentum in the y direction didn't change. So does that make sense to you guys? You following all this? Is this okay? Does it? Yeah, good.
Yes.
So even if it had a z component, it would be the same thing. If that particle was coming towards us and hit the wall, it would still be coming towards us. It's because the axis here is perpendicular to the x-axis. That's why it's the x component only that changes. So even if it had a z component, this z component would not change. So regardless, you know, if it had an x, y, or a z component, this delta mv over delta t is 2 mvx over delta t for any x, y, any particle moving with any x, y, and z components, okay? This is for particle with a velocity vector x, vx, should say, vy, vz, moving, or I should say striking a wall perpendicular to the x direction. Okay, so this is the force per collision. Okay. All right, so now that's the force per collision. So we want to know how many collisions, how many molecules will hit the wall in a time delta t. Okay, so how on earth do we do that? Well, we have to start by talking about how many molecules are in the container, okay? So the molecules in the container are determined by what we call the number density. So the number density, let's call that D, that's just the number of molecules per unit volume. And this is determined by, you know, how many moles you have in there. If you take the moles and you multiply it by Avogadro's number and divide it by the volume of the container, that's what the number density is. So we're assuming that these things are known, okay? That it's some container with a known, you know, number of moles. Okay, so the next thing becomes, you know, how many of those molecules will hit the wall in a time delta t? So let's get back to the question of how many molecules will hit the wall in time delta t. All right, so here's the thing. It's a great way to think about this. If molecules travel with an x velocity, so an x component of their velocity, which I'm calling Vx, and they're heading, and they're traveling, well, let's see, let me say this right. So if they're traveling with an x velocity, Vx, then how far in the x direction will they travel in a time delta t? How far will they go? and of course I mean in x direction, in a time delta t. So if you take Vx and you multiply it by delta t, that's the distance, at least in the x direction, in the time delta t, okay? So that means that if the molecule is within this distance of a wall, it should hit that wall in time delta t. Does that make sense? Think about that. I'm actually going to draw a picture. Here's a picture. There's a wall. Okay, and let's think about, let's talk, this is the x-axis. And I'd like to focus on the rear wall here. And here is a distance, Vx delta t, right? So all the molecules that are in here, okay, they're traveling with the speed Vx delta t. Will they all hit this wall in delta t? Did you think about that? What's wrong with this statement? Will they all hit the wall? They all have a velocity Vx in the x direction. In time delta t, they'll travel this distance here. So if I'm a molecule over here and I have Vx, I'm going to hit the wall within that time, right? Because I can travel a distance Vx delta t in that time. But will all the molecules in this red volume, will they all hit the wall in time delta t? Anybody? All right.
Yes.
Go ahead. Well, okay. Are they all traveling towards that wall? Half of them are going to be traveling the other way, right? Because we have random motion here. So random motion says that half of the molecules in the red volume my computer's too hot. Can I unplug this? What's going to happen if I unplug this? I don't know if that'll make any difference, but well, we can still talk. Half the molecules are going to be traveling towards the wall and half are going to be going the other way, right? So half the molecules in the red volume will hit the wall in time delta t. And half of them will not because they're going the other way. Do you see that? Let me close this and open it again. Just a few technical difficulties here. It's really OneNote that's the problem. Yeah. Sorry, this is what happens because my other computer didn't work. Oh, well. I may have to come back. Here we go. Try it again. All right, so are you following this okay? Yeah.
Yes.
So if they're traveling with a velocity, x velocity vx, they'll go a distance vx delta t in a time delta t. If they're traveling towards this back wall, okay, then they will hit that wall in time delta t. If this is if, you know, I've drawn the vx delta t on there. All right, so so that is to say that half the molecules in this red volume will hit the wall in a time delta t. So all I need to do is calculate how many molecules are in that red volume, and I will know when I take half of them. I will know how many of them will hit the wall, so I will have a total number of collisions. So what is that volume? So what is that volume? Well, I'm going to call this here A for area. So A times Vx delta t, right? So it's this length times this area here, okay? That's going to be the volume. So that's the volume, red volume. And what is the number of molecules in this volume? Well, I told you that D is the number density, right? That's the number of molecules per unit volume. So if I take D and I multiply it by A Vx delta t, so what I've done is I've taken the number of molecules per unit volume and I multiply it by, I guess I would call it the volume of interest, which is that red volume. And what that gives me is the number of molecules in the red volume. And that's what I want, because half of those molecules will collide with that wall in delta t. So I'm going to take dA Vx delta t divided by 2. And that's the number of molecules that will hit the wall in the time delta t. Okay. So what is the pressure going to be then? So pressure let me put in what the density is first. So the density is the moles times Avogadro's number divided by the volume. Okay, so I'll put that in. So that makes this N times Avogadro's number over V times A Vx delta T over 2. So this is the number of molecules that will hit that wall in time t. So this is that number of collisions, because remember, going back, pressure was the number of collisions times the force per collision over the area. Okay, so this is the number of collisions. So if I put this together with the force per collision, it's going to start looking a little complicated, but I'm going to do it anyway. I have N, and I'm just copying this down from here. Okay, over V, A, Vx, delta T over 2. So that's the number of collisions. This is the force per collision now. Now the force per collision was 2 mvx over delta T. Well, I can already see that I'm very happy that the delta T's are going to cancel. A lot of things are going to cancel. The area cancels. The 2's cancel. Hey, I'm going to put these Vx's together. So I have P equals, this is the pressure, N, Avogadro's number, and then I'm going to put the mass, and then the square of the x component of velocity over the volume. It looks a lot better, but there's a few things about it that we can simplify a little bit. First of all, what is this? That's the molar mass. It's Avogadro's number times the mass of a particle. So we actually have two expressions. P equals, I'm just going to leave the Avogadro's number there. We have this one, and then we have this other one. And we could do different things with these, so we're just going to keep that aside. And I want to sort of pause and like consider what we have so far, okay? So what this says, and I could rewrite it as PV is N Avo mvx squared. Okay. The PV product of a sample of gas is proportional to the x component of the velocity squared. Okay, so is there any problem with this? You know, it's very odd to have an expression that depends on one direction when you have a sample that has 3 equivalent directions and there's nothing special about the x direction. So there's a couple of problems with this. First of all, what is it about the x component of the velocity? That's the only one that ended up in this expression. I mean, if I had started my derivation talking about a wall perpendicular to the y-axis, then this would be Vy, right? There's got to be a way of getting rid of the x, y, or z there, okay? So I'm bothered by the fact that there are 3 components and there's nothing special about x. So that's one problem. But the second problem is, it's not something you get by looking at this expression, but it is a problem nonetheless. And that is that molecules in the sample do not all move with the same speed. Okay? They move with a whole range of speeds, okay? So I'll talk about that. What we're going to actually have to do is the derivation becomes less rigorous, you know, because I'm going to have to really, I'm just going to have to deal with averages instead of saying they're all moving with the same speed. So let's see. So the first thing I'm going to do is I'm going to take my Vx and I'm going to change it to the average value of Vx. And of course, I didn't prove this. But that's why I said this derivation is sort of not as advanced as it could be. Okay, so I'm not doing anything about, I'm just going to simply change Vx to average Vx, acknowledging the fact that molecules are not all moving with the same speeds. So PV equals N Avogadro's number times the average. Hold on. Oh, it's a squared. Actually, sorry, I forgot the square. I'm going to change that to that. The average squared velocity. And the other form of it was PV is N times the molar mass times Vx squared. All right, so that's the problem with the average. And what about this X? Why is X so important? And the answer is it's not. There's nothing special about the X direction. So how can I eliminate this X? All right, so the way you can do that is if you think, here's a typical velocity vector. It's got 3 components. And we're talking about the squared. How do you square? What is V squared? What's that? Hold on. Does anyone know what the square of a vector is? Yeah, I'll tell you what it is. So V squared is the sum of the squares of each component. That's sort of the definition. If you've taken Calc 3, it's the dot product of a vector with itself, but I know you haven't, so that's fine. So this is what the definition really is of the square of a vector. So the average V squared for all the particles is the average of this sum. So it's basically averaging all the X components, each squared, plus all the Y components that have each been squared, and all the Z components that have each been squared. And if you take an average of a sum, well, that's the sum of the averages. So I could really write this way. Because all an average is adding and dividing by a total. So it doesn't matter if I average all the squares of X and then all the squares of Y's and all the squares of Z's and average those, or if I do everything all together. It doesn't make any difference. So this is something that's going to be true of any sample. Now, because the motion is random, that means that there's just as much motion in the X direction as there is in the Y direction or the Z direction. And so really, these are all the same. So V squared is 3 Vx squared, right? These are all Vx squared is equal to Vy squared is equal to Vz squared. All right, so that means that Vx squared average is just 1/3 V squared. And that's really nice because I can go back to the equation I had, and instead of having an average of Vx squared, I can just put in 1/3 of the average V squared, and that makes me feel a lot better because then I know that my formula isn't prejudiced to something about the X direction. So I have PV equals NM times Avogadro's number times 1/3 V squared. A second. Did my microphone change? There's no camera on. Did my microphone change? I don't know. It says it changed my microphone.
No, we can hear you.
Yeah, but now it's not recognizing the camera anymore. I don't care. You don't have to see my face.
We can see you.
Yeah, we see you.
For a minute you couldn't, but all right. So so now I have PV is 1. So it's N. Where is it? M, Avogadro's number, times 1/3 V squared. Or the other version is PV is NM 1/3 V squared. All right. All right, so I'm going to put the third in the front. Actually, I'm going to move this around a little bit because I'm going to put this mass over here. And then you could see where this is going, I hope. So what does that almost look like to you? I'm just going to work with this part of it. What is 1/2 mv squared? What is that? All you people who've taken physics.
Is that 4? No, not 4.
It's kinetic energy, 1/2 mv squared, right? Okay, so KE in brackets, and I use a lowercase k and a lowercase e, and I'll tell you why in a minute. The average kinetic energy would be the average of 1/2 mv squared. That's for one particle, right? This m is the mass of one particle. That's why I use a lowercase kinetic energy, because later on when I do it for a mole, I use a capital Ke, all right? So this is for 1 mole, no, 1 molecule. Now, this guy is a constant, and you could always take a constant out when you're doing an average. So this is the kinetic energy on average kinetic energy of 1 molecule. So if I take my PV is 1/3 N times Avogadro's number, mv squared, all right? And I just move this m over a little bit, and I put in a 2 and a 1/2, okay? If I can do, I get 1/3 N times Avogadro's number times 2, so I'll put the 2 over here, 2/3, times the average kinetic energy, okay? Now, if I take Avogadro's number times the kinetic energy of 1 molecule, taking this together is the kinetic energy of 1 mole. And I call that average, of course, this capital Ke. I use capitals for 1 mole. So PV equals 2/3 N Ke. Okay, this is a, hue, right? This is a really, really nice result, okay? It says that the pressure volume product for a gas sample is proportional to the average kinetic energy of molecules. And there are 2 ways that you can proceed with this. And some courses teach you one way and some courses teach the other. So there's 2 ways to conceptually proceed with this. Okay, one way is to make a 4th postulate. And the 4th postulate of the kinetic theory that you often see And that fourth postulate would be that the average kinetic energy is 3/2 times RT, R being the gas constant in joules per mole Kelvin. That's 8.314 joules per mole Kelvin. And this, of course, is the temperature in Kelvin. So I personally don't like that way because, you know, that sort of comes from outer space, okay? So what I like to do is to combine this with the ideal gas law, PV equals nRT. That's a macroscopic observation. So I like to take the macroscopic observation, that's how they got that law, and combine it with this result here from the microscopic proof. So if you do that, if you take PV equals nRT, and PV is 2/3 N times the kinetic energy average, you end up with nRT equals 2/3 N KE, N's go, and you end up that the average kinetic energy is 3/2 RT. So it's really just a conceptual difference. You can either postulate that the kinetic energy is 3/2 RT, and if you do that, you can actually derive the ideal gas law, right? Because if you plug in 3/2 RT here, right, then you end up with PV is nRT. Or you can combine this giant thing we just got with the ideal gas law and end up with the relationship between temperature and average kinetic energy. So, but either way you do it, this is a huge result and a way of thinking about what temperature even is, you know. So this tells you that the temperature is a measure of the average kinetic energy of that sample. Is a measure of the average kinetic energy of the sample. Okay, and that's the big result. And I'm going to stop there, I think, today.